Hello, and welcome to the video accompaniment for Chapter 5, Section 3. In this one, we're talking about functions, which are really just a special kind of relation. In this video, or after this video, you should be able to recognize when a relation is a function, what to look for to determine that, be able to find the domain, codomain, range, and the image of a set under a particular function, and understand what all of those words mean. Be able to represent a function using either a diagram, so blobs and arrows, or a graph, and that's just the graphs that you're familiar with, and be able to determine a composition of functions when given a pair of functions, and be able to evaluate that at different points and understand the notation that goes along with that. If you haven't already, make sure you read through the section, familiarize yourself with the definitions, and look through a couple examples. And hopefully this video will help you understand that material a bit better. All right, let's get started. Since a function is really a special kind of relation, we should be able to pick out which relations are functions and which aren't. This will also help us better understand the definition of a function. So let's look at a few examples here. So I'll give you these two sets. A is just the elements 1, 2, 3, and 4, and B is the elements W, X, Y, and Z. And I'll give you three relations here. And we want to determine which, if any of the relations are functions. So before I put those functions up there, remember the definition of a function is a relation such that everything in the domain, the first set, so the set A here, is associated with exactly one element of the codomain. So that is, every element of A is assigned something in B, and it's assigned no more than one thing. So everything in A has exactly one thing in B that it's assigned to. So we'll keep that in mind as we go through this. So there's first relation, second relation, and third relation. And I'll go ahead and put little dividers up. And let's just go through these one by one and determine if the relation is a function or not. Let's see if it meets that definition of function. Now, one thing I think is helpful with these relations and determining if they're functions is drawing diagrams. So what I'll do for this one, maybe you can already tell that R1 is not going to be a function. But let's draw a diagram and see why. So I'll go ahead and put my blobs down. Here's A, the set A, and here's the set B. There's my elements 1, 2, 3, 4. I'll label them in a second. Here's my elements W, X, Y, and Z. And I'll label them. So this is 1, 2, 3, 4, W, X, Y, and Z. And now we'll do just like we did in the last video. For every ordered pair here, I'll draw an arrow from the first coordinate to the second coordinate. So 1 goes to W. 2 goes to X, looking good so far. 3 goes down to Z. 4 goes to Y. And 1 goes to Y. So this relation does not meet the definition of a function. And the issue here is that the element 1 has been assigned two distinct values of B. We can see that in the diagram because there are two arrows coming off of 1. So not a function, since 1 is assigned to W and to Y. It has two. If we think of functions as input and output, then the input 1 has two outputs. So that's no good. That makes this not a function. This is just a relation. All right, let's take a look at R2. I'm going to start by drawing my blobs again. 1, 2, 3, 4 are my elements of A. 1, 2, 3, 4, my elements of B. I'll go ahead and label these again. Here's 1, 2, 3, 4, W, X, Y, and Z. All right, let's draw our arrows. 1 goes to W, 2 goes to X, 3 goes to Y, and that's it. That's the whole thing. So this is, again, not a function. What's the issue here? It's not the same issue as the last example. That's why I picked it. Because we can see there isn't 2 arrows coming off of a single element of A, like what happened in the last example. Instead, this element 4 is not assigned to anything. That makes it not a function. So I'll say not a function. The element 4 is not assigned any B. There's nothing that it's assigned to. All right, let's take a look at R3 here. I'm going to draw my blobs again. Or potatoes, if you like that term. 3, 4, W, X, Y, Z. W, X, Y, and Z. All right, there we go. Let's compute this function. So 1 goes to Z. 2 goes to Z. 3 goes to Z. Oh, what a function. Or what a relation. And 4 goes to X. So we can see here that everything in B is not, doesn't have something assigned to it, right? W and Y are missing things. They don't have anything assigned to them, and Z is hit multiple times by elements of A. Despite those sort of oddities with this is a function. Remember, with a function, we need to check the elements of A. Is every element of A assigned exactly one element of B? And yeah, that's the case. So what we're looking for in the diagram to determine if a relation is a function is that every point in the left set has an arrow coming off of it. And in particular, it has exactly one arrow coming off of it. So it's okay that Z is hit a lot of times. That's all right. As long as, well, yeah, full stop. It's okay that Z is hit lots of times. As long as every element of A has exactly one arrow coming off of it, we're good. This is a function. All right, in the next one, we'll talk about these terms, domain, codomain, range, and image, given a particular function. So let's give ourselves an example here. Remember, when we know we have a function, or when we're defining something that's going to turn out to be a function, in this case defined by a rule that associates every element of the domain to every element of the codomain, by this rule, we use this notation. So f is the name of the function, and then I'm specifying here the domain and codomain. So domain is all the inputs, and codomain is all of the possible outputs. Doesn't mean that everything is hit in the codomain, just that that's where everything that's hit lives. And so we already answered 1 and 2 here. The domain of f is Z. That's easy to pick out, because if it's defined like this, we know that's the domain, and this is the codomain. So maybe you haven't heard that word before, codomain, or maybe you've heard it and you've never really understood exactly what it meant, but that's all the codomain is. It's where all the outputs live. It's a set that contains all of the outputs. Codomain of f is also the integers. So what about the range of f? So I get, whenever I teach this topic, a lot of people confuse the range and the codomain. They think that this thing here is the range. But really, we know that's what's called the codomain. The range is everything that is hit. So I'll write it like this: range of f is the set of all outputs, so I'll call them f of n, such that n is in the domain. So it's the set of all those outputs. In this case, I can rewrite that. I know the formula for f of n. I know my rule here, so I'll replace f of n with 2n. So it's the set of all 2n where n is in Z, and that should be very familiar to you. That is the even numbers, the even integers. And so while the codomain is all the integers, only the even integers are going to be hit by this function f. And so we say that that is the range, so the set of outputs. And image is very similar. So another way we could have written the range here, we could have also written this as, let's say, f of a set. I'll let e be the even integers here. So we could have written up here f of the integers is the even integers. So that's okay. We can plug, in some sense, we can plug sets into functions, and what comes out should be another set. So with the range, we're doing that for the entire domain. We're looking at all the outputs of the domain. For the image of a function, or image of a set under the function, that's just, it's all the outputs of these inputs. So take all of those inputs and compute their outputs and then collect those all in a set. And the notation here we can use is f of, it's like we're just evaluating the function at a set. We know that that really means the set of all outputs of these input values. So this would be the set. All right, when I plug -1 in, I get -2, so -2 is in there. When I plug in 0, I get 0. When I plug in 1, I get 2. And so this is the image of the image of the set -1, 0, 1 under f. So that's the deal here for domain, codomain, range, and image. Let's move along. Let's take a look at another example. Here we'll look at the function f from with domain the real numbers and codomain the integers, and that function is defined using this rule that f of n, the output of the real number n, is the floor of n. So if you look closely, you'll see there are some little dongles on these bars that might look like absolute value. It didn't render very well in the PowerPoint, but this, maybe I'll blow it up. This is really the floor of n. And how do we compute floor? This is one of our common functions that we'll start seeing more of in the class. Floor is the greatest integer that is less than or equal to n. So biggest integer that is biggest integer, I don't know, I'll call it y, that has y is less than or equal to n, such that, I should use some proper grammar. Biggest integer y such that y is less than or equal to n. This is also called the greatest integer function. And so it'll only spit out integers. It only spits out integers, hence our codomain here is the integers. So let's maybe try it. So like f of 0.01 would be 0, because 0 is, there's lots of integers that are less than or equal to 0.01, right? -1, -2, 0, -1,000,000. But of all those integers that are less than or equal to 0.01, we take the biggest one. And so in some sense, this is like rounding down. For example, f of pi would be 3. What about negative numbers? What about if I had like f of negative 0.1? Now, if you're thinking rounding down, you might think this is 0. And so rounding down is sort of, I mean, it's helpful, but sometimes it can lead to a misunderstanding. So remember the definition of it. It's the greatest integer y, such that y is less than or equal to n. That is, the output should always be less than or equal to the input. And so 0 doesn't make sense here. 0 is bigger than negative 0.1. In fact, this is negative 1. That's the next integer down from negative 0.1. And maybe let's do one more. F of negative 100.9 would be, again, don't just think round down. That might lead to you thinking that's that this should be negative 100. Instead, this is negative 101. Biggest integer less than or equal to n. This pairs well with the ceiling function, which is the least integer that's greater than or equal to a particular input. And so that kind of goes along with this, but in this one, we're just looking at the floor. So we'd like to graph this function and determine its range. Now, a graph of a function, if we're dealing with nice discrete sets or finite sets, we could totally use those blobs that we've been using, or the potatoes and arrows that we've been using. But for something defined on a continuous set, like the real numbers, that's going to be really, really hard to do. Instead, what we'd like to do is just use a graph like we're familiar with, like from calculus or algebra. And so what I'll do is I'll draw some axes here. I don't like this drawing. All right, let me try again. There, that's a little better. Just like I do, you should strive for neatness. I know I'm always not super neat, but when I do something that looks, I don't know, just really not neat, I'll just redo it. You know, it's always better to be clear rather than save time. And so for a graph like this, while we usually write like integer values here, we know that all the values in between are also there and also meant to be graphed. -1, -2, -3, -4. I'll just go 1 to 4. 1, 2, 3, 4, and -1, -2. And maybe you haven't graphed things in a while. And so this is a nice reminder of how to set up your axes and then graph a function. I'll graph this one in, I don't know, how about I use blue? All right, so remember, even though we've just written integers down here, our function is defined on the entire domain of the real numbers. So every little real number between, say, 1 and 2 is between 1 and 2. And so when we graph this, it doesn't just look like a set of points because there's so many points that it turns into a line. That's the idea. And so for any real number, now I'm looking at these real numbers between 0 and 1. When I take the floor of that, I should get 0 out. But what happens at 1? Remember, this is the biggest integer less than or equal to the input. And so f of 1, yeah, I guess I didn't do any examples of that over here, but f of 1 is 1. F of 0 is 0. So if the input is an integer, it just returns that integer. So between 0 and 1, we should just get 0 out, and then at 1, we should get 1. So I'll draw it like that with an open circle here at 1. And then integers between 1 and 2, they'll all output 1, and then when I get to 2, it'll output 2. Same for 2 to 3. When I get to 3, it'll output 3. When I get to 4, it'll output 4. Why is it doing that? Right, notice why I'm drawing the open circles, and that's because, well, f of 4 is not 3, although it certainly looks like it might be 3 by the line. And so I want to say the line stops right there at 4, and look at the dot for what the function's value actually is. Do. And we could continue on, and then at 5, it would be up there, and so forth. Real numbers, we know at 0, we should get 0. So I'll go ahead and mark that. At -1, it'll output -1. But for, let's see, everything in between, so like -0.5 is between 0 and -1, that'll output -1, like we talked about. And so we'll continue our graph down here. -2 should output -2. And we'll just continue along our merry way for the floor function. So this is a graph of part of the floor function. So the floor function just between these values that I have on the axes here. And then the other question is, what about its range? Well, what's the range of this? What are all the things that are hit by this? Notice that every integer is going to be hit by this function at some point. And so the range is the entire codomain. But this is really, we picked the very smallest codomain possible for this function. The range of f is the codomain. So sometimes the codomain and the range coincide. And what we'll see that that's actually a really nice property in the next section. When the range and the codomain coincide, the function is said to be surjective or onto. It covers the whole thing. And so that's a very nice property that this function exhibits. All right, let's move along. All right, what do we have next? Well, what about composing functions? This is something hopefully you've seen before, but let's talk about it in a discrete case like this. So f from A to B, defined by just associating every input exactly one output. And G from B to C, defined by, again, associating every input now of B, an output in C. So there's a nice trick with these potato and arrow diagrams I've been doing, the blobs and arrows, for compositions of functions. So this notation is a bit confusing for people sometimes. G of f. That means normally we read left to right, and so you'd think G would be the first thing that's computed. But actually, just the way function notation works, and by the way, other countries do this differently. There's sort of a just convention that this is how we write functions here in America, and many other places do it like this, but some countries don't. Some places don't. So this is not G first. This is actually F first. We'll do F first, and then we'll do G. So it's sort of the opposite of what we might think it should be. And again, that's just convention. We could pick to do it the other way, but then we'd sort of be flying in the face of all these textbooks that will be that you'll use. So what I'll do here is I'll draw a graph of f and g, and so I'll need to include all three of my sets here. So we have A, we have B, and we have C. A, B, C, D, little A, B, C, D. 1, 2, 3, 4, and then we have X, Y, and Z. And let me write down, so this is A, B, C, D. 1, 2, 3, 4, and X, Y, and Z. So I'll first just graph F and B. So F is going from A to B, and G is going from B to C. Maybe I'll use some different color for my arrows. Maybe I'll use blue here. All right, so what does F do? It sends A to 1. It sends B to 1. It sends C to 2. And it sends D to 3. So that's a function because everything in A has exactly one arrow coming off of it. So it's definitely a function, even though 4 isn't hit. And then maybe I'll use a different color for G. What does G do? G sends 1 to X. It sends 2 to Y. It sends 3 to Z. And it sends 4 to X. So again, a function because everything in B has exactly one arrow coming off of it. Now I could go through, right, each of these and figure out what's G circle F of that thing. So I don't know, maybe let's just try this. So let's figure out, it says to do the second, but whatever. To hell with that direction. Let's do G circle F of A. Now what this means, G circle F is a function in its own right. Hence why I have parentheses around this. G circle F is the composition of G and F. But what this means, the definition of this is apply G to the output F of A. So that's what G circle F of A means. It means G of F of A. And so what is F of A? We can use this definition to evaluate. F of A is 1. And so G of F of A is the same thing as G of 1. And G of 1 is X. And so G circle F of A is X. And so we could do that for each of these, and that would tell us how G circle F works, right? So notice that G circle F is a function from, so F goes from A to B, and then G goes from B to C, that this is a function from A to C. So the inputs are in A, I evaluate F at those, and then evaluate G at that output, and I get something in C. And so we could do this for each of these, and this would tell us our rule for how G circle F works. But notice something with the arrows. So I'll draw 2 more blobs here for G circle F that really, A and C, and this is G circle F, and I'll plot my elements down, A, B, C, and D, and X, Y, and Z. And I'll use some other color. How about I use, I don't know, red for this one. So what I can do is I can follow my arrows. So A, I mean, we computed that, we know it should go to X, but let's see that. So I'll trace my arrows up here. So A goes to 1, and then 1 goes to X. So I just followed both arrows. I put them on, I went tail the head. And so A goes to X. B, well, I'll follow the arrow. B goes to 1, and 1 goes to X. So B goes to X. C goes to 2, and 2 goes to Y. So C goes to Y. And lastly, D goes to 3, and 3 goes to Z, just following those arrows. So D goes to Z, and that's how I can determine my function G circle F. As long as F and G are functions, this composite function will also be a function. Notice we couldn't compute F circle G here because that doesn't make sense to do, right? F circle G, well, G goes from B to C, and F goes from A to B. So this doesn't make sense to do here. right? G goes from B to C. So if I want to compose something with G, its domain would have to be C. Likewise here, the domain of F was A, and the codomain of F was B. So if I wanted to compose F with something, that function would have to have domain B. So in order for this composition to work, the domain of the first function must match up, or sorry, the codomain of the first function here, F, would have to match up with the domain of the second function, G. So that's the deal with that. However, when functions are defined on the same set, so like functions from A to A, we can compose a function with itself, and we have a lot more freedom there. So let's take a look at something like that. Let's take a look at one more example of composite functions. This time we'll have two functions, f and g, both defined from the real numbers to the real numbers. Notice that when this is the case, when the two functions are defined on the same sets and the domain matches the codomain, that we can compute both f circle g and g circle f, that those will be well defined because the domain and codomain match up, right? The domain of f, or the codomain of f, say, is the real numbers, which is the same as the domain of g, and so we can that's, it's defined. The other thing I want to point out in this is that when our functions are given by rules like this, we can, by using the definition of composite, write a rule for the composition of f and g. And so let's see how that works. So f circle g of x, so an arbitrary input x, what happens to that? Well, by definition, this is f of g of x. Now, g of x is x squared, and f of that, well, let's just write that out. So this is f of x squared, and then f of x squared, so that would be, f says to take sine of the input, so this is sine of x squared. And so that tells us that in general, f circle g of an input x is sine of x squared. So that's how we can determine the rule for the composition. Likewise, we can do g circle f, and so that would be g of f of x, which is g of sine of x, and so that's sine of x squared, because g tells us to square the input. And so in total then, g circle f of an arbitrary input is sine of x squared. And so now it wants us to compute these. So notice that these two formulas don't look the same, even though, right, we did f circle g and g circle f. You might wonder if the commutative property holds, or maybe you're familiar enough with composition that you know it doesn't always. Certainly these functions look a lot different. Let's evaluate them at some different values now that we have rules for them. So let's compute f circle g of 0. So that would be sine of 0 squared. 0 squared is 0, sine of 0 is 0, so we get 0 for that. And then we'll do g circle f of 0 as well. So that is sine of 0 squared. Sine of 0 is 0, we square that, we get 0. So at least at 0, these two functions do match up. Does that mean they're the same function? No, in order for two functions to be the same, their outputs have to be exactly the same. They have to be doing exactly the same thing for all possible inputs. Here we just have a particular value that gives us the same output. So this is, again, back to these quantified statements. It needs to be true for all inputs. And so just showing one input is true doesn't prove that they're equal. So let's actually look at one more. Let's look at f circle g of pi over 2. And g circle f of pi over 2. So here this would be sine of pi over 2 squared. So that's sine of pi squared over 4. What is that exactly? Well, let's just leave it like that for now. And G circle f of pi over 2. So f of pi over 2, let's do that. So this would be sine of pi over 2 squared. Well, sine of pi over 2 is 1. Square that, we get 1. And so I guess for this one, we could grab our calculator and compute this, but we can say for sure that this is not equal to 1. That's a true statement. It's definitely not equal to 1, while G circle f of pi over 2 is equal to 1. And so from just 1, right, to say that they're not the same thing, all it takes is one input, making the outputs different in order to conclude that. So we can say that f circle G is not equal to G circle f, that they're not the same function. All right, that's it for this video. I will see you next time.